Let's say you have a line segment of length 10. When you pick two arbitrary points and break up that line segment into three pieces randomly, what's the probability of those three line segments forming a triangle? This is a quiz that once my friend told me about. The setting is simple, but it's kind of difficult to find where to start from. I asked him for a hint, and his answer was, when you're trying to deal with the probability of a continuous value, it's usually a good idea to try to express the probability with area. That was it. That was a starting point that brought me to the answer that involves probability in geometry in a beautiful way. So, let's write down what this quiz is saying. It says, you have a line segment of length 10. When you break up that line segment into three pieces randomly, what's the probability of those three line segments forming a triangle? So, if we express the length of those three line segments with x, y, and z, x plus y plus z is always 10. That is simple. But what about the forming a triangle thing? How can we put it into a formula that we can start computing? Well, let's think about an easy case. If the original line segment breaks into three identical lengths, they will form an equilateral triangle with side length 1/10 each. This will count as a case where it will form a triangle. Now let's think about a very different situation. Let's say the line segment breaks into three line segments that have a length of 1, 8, and 1. Then we're screwed. Those two little line segments that connect to the edge of line with length 8 have no way to touch each other. There is absolutely no way that they can form a triangle. So it seems like there needs to be a balance in the distribution of the length. Well, in fact, if you look up on Wikipedia or any kind of math textbook, it says that the sum of the length of any two sides of a triangle must be greater than or equal to the length of the third side. So, we can write it down as the following expression. If we describe the length of the broken three line segments as x, y, and z, they have to be like this. X is less than y plus z, y is less than z plus x, and z is less than x plus y. Another condition that may not be clearly obvious, but obviously clear, is that any of these three lengths should not have a negative length. We are breaking down a line segment that has length 10, so we don't want to consider a side length with a negative length, at least not in a problem like this. So, we can write it out as the following expression. X is greater than 0, y is greater than 0, and z is greater than 0. Therefore, we can conclude like this. Now let's look back at this expression, x plus y plus z equals 10. This means that you can write it in the following way too. Very simple. If you add y and z, that has to be 10 minus x. So if we plug that into the other inequality, we start to get a better view of this problem. So, x must be less than 5. Similarly, if you do the same for y and z, you get this. So these three inequalities could be written as following. X must be between 0 and 5. Y must be between 0 and 5. And z must be between 0 and 5. Now this looks much simpler than it was, and it goes well with what our intuition suggests. When you want a line segment of length 10 to break into three segments and form a triangle, none of those small line segments should exceed length 5. Great. So to sum up where we are, these 2 or 4 expressions are what we got so far. Now, since we have 3 variables, x, y, and z, let's see what we can get if we put those into a 3-dimensional graph. To show that, we now open our friend Desoms. So this is what those 3 inequalities look like in the 3D space. It looks like a cube with side length 5, and the vertices sit on 0, 0, 0, 0, 5, 0, 5, 5, 0, 5, 0, 0, and 0, 0, 5, 0, 5, 5, 5, 5, 5, and 5, 0, 5. Now what about the other condition? The initial expression x plus y plus z equals 10 can be drawn like this. It can be expressed as a big triangle where the 3 vertices sit on 10, 0, 0, 0, 10, 0, and 0, 0, 10. So, thanks to Desoms, we now have 2 objects that represent the conditions. So the problem now is to find the area where this big triangle and this cube intersect, and compare that intersection area with the area of the big triangle. Now, computing an area of a triangle leaning inside an XYZ space could be very difficult, but in this case, you don't have to compute the exact area. In fact, we're almost there to get the answer. If we look into just one of the planes, let's say this YZ plane, this red line is the side of the big triangle, and this blue square is one of the faces of the cube. And you can see this red line is tangent to the blue square. And since the line is drawn from 0, 10, 0 to 0, 0, 10, and the vertex of the squares located at 0, 5, 5, this vertex is clearly the midpoint of the line. And since this is identical to the rest of the planes, you can see that the big triangle intersects the cube with this green equilateral triangle. So, this view right here is the answer. We have the big red triangle that represents all the possible combinations that you can have when you break a line segment of 10 into 3 segments, and the middle green triangle represents all the possible combinations that those 3 segments form a triangle. And since the middle triangle vertices sit on the midpoint of the big triangle, the area has to be 1/4. So, the answer to that question is 1/4. After going through the explanation, I think it's safe to say that this is not a difficult question at all. You may not need a high school math knowledge to solve this problem, but the great thing is that you can just visually see the answer. This triangle right here represents what we were looking for. Of course, I owe a lot to Desoms in order to create these beautiful graphs and shapes, but with the help of modern tools, you can find the answer to the simple question in a visual, intuitive, and beautiful way. Hope you like this solution. Thanks for watching.